Okay, here we go. The title I was given, that's from many years ago, is the long-term evolution of geospace. So we've got to achieve two things. One, we've got to all agree on what geospace is, and then what do we mean by evolution, okay? So let's just proceed. I'll have a couple of takeaway messages, and Lika alluded to this one. These two ideas as we go through today, maybe you'll have your own ideas, but what is it that heliophysics can learn from stars? And this morning, Greg touched upon that too. What kind of information can you get, especially as our measurement techniques improve about things like the solar wind and others. We only have one star, and it's not evolving very rapidly. So in our lifetime, it's a constant, as we've heard this morning. But then the other thing is this other side of it. We know a heck of a lot about an interaction between a star and a planet and an atmosphere. It's one particular geometry or configuration or system. But nonetheless, we kind of know what works and doesn't work and what kind of processes must be going on. So for example, how many of you heard the Goldilocks zone? Yeah, I mean, when people talk about exoplanets, they have this one word, Goldilocks zone, and that's supposed to make it habitable, and that's BS, as you might expect. There's a boatload of stuff going on, and it's to do with our knowledge of the physical processes that emanate from a star, influence or interfere with an atmosphere, and then lead to other components of that atmosphere. If they're technologically kind of advanced civilizations, they might have technologies like cell phones and other things. But so our ionosphere plays a role. Okay, so that's a takeaway as you're going through. Just mull over how much we really do know that would be relevant. And this is then the other part of the SAIR. What good is it to us? Well, in our environment, what it does is it protects our lower atmosphere from flares, aurora, and magnetospheric electric fields. All of these, because of our Pedersen conductivity and the cross-sections of absorption for the photons and the auroral electrons, they all fall into this one region. And although they're all very interactive and affect each other, the energy deposition there is in a place where if you go lower down, the densities are huge. So the trickling down of energy from this region doesn't do any good lower down. Going upward, of course, we have the problem that all of a sudden the amount of energy we're putting in can modify what's above us significantly. And that's what we'll be talking about a little bit today. Okay, how did early humans know there was a geospace around the Earth? Okay, so we see, the sun and whatnot, but how do we know there was a geospace? Thank you. Okay, this is for Alan.
When I was a lad, a tiny wee lad, my mother said to me, "Come see the northern lights, my boy, they're bright as they can be." She called them the heavenly dancers, merry dancers in the sky. I'll never forget that wonderful sight, they made the heavens bright.
I'm almost tempted to say all together. We could let this go on for 10 minutes. Okay, so here we go. How many of you, once again, who's not seen this before? The aurora, okay? The aurora, this is, words like stable east-west arc might be applied to this, but there's nothing stable about it. You can see it jittering around. But in the early evening, when you're up there, watching as this arc forms. It's east-west aligned, and it's moving a little bit. In some cases, there are multiple arcs, but this goes from one kind of horizon across the top of you to the other horizon. It's coming in from the north if you're at kind of mid-latitudes. But I've got a second one. This is if you're really lucky and you're standing underneath a bunch of field lines when this thing breaks up as the substorm kicks in. You've got this. The only thing wrong with this is your head hurts like nothing. Your neck, as you watch this for 10 minutes, you're just in agony. But this is a corona breakup, if you like, terminology, but it's part of the substorm. You can see that the field lines kind of emanating from a point, if you like. What other phenomena in terms of observational astronomy might have this effect if you're watching it? The old pictures or the old sketches of these things tend to indicate this. What kind of shower? Meteor showers. They all come from a point and it's coming past you. Okay, so that's the fun part. Now we get serious. Okay, this was, and I appreciate all the inputs you've given me. Nick shared with me some more. So I asked you what was aurora called in your language. Post an English translation, so I appreciate that. The name of your country so we can connect the dots. And then describe or give a traditional explanation for what it was called in your culture. You saw the one from Scotland, just referred to them as the Heavenly Dancers. And Alan, you gave us version in Gaelic, didn't you? No. Well, I'm Polish-German, so I couldn't anyway. Yeah. They don't know better, so they all agree with you. Well done. They're which? The nimble ones. Okay, so that's another description of how this dance is around. Okay, I sure hope you'll make it a point to go and see the aurora one of these days. You've all seen rainbows, and that's boring. Okay, so let's kind of move on. Let's do a little history. So what we knew, and of course what we knew about geospace did come from the aurora and observations thereof initially. So there appears to be some evidence that the macaronis for this culture 30,000 years ago may have been an attempt to represent the aurora. Most certainly as we get into this period BC, it's fairly clear that the various civilizations did, the Greeks, the Chinese, the Babylonians, they did all try to represent these particular phenomena. At mid and low latitudes, often it's a huge red aurora. It's pretty scary. The day they launched the space shuttle for the first time was on a Sunday, the 12th of April. And when they launched it, there was a ginormous red aurora across mid-latitudes. And of course, even, how long ago was the shuttle launched? About 20, 30 years ago, 40 years ago. So it's in our time. But the newspaper articles indicated that doing this on a Sunday led to retribution and the red aurora. And it took about a week before Logan space scientists were able to correct the article that had been published erroneously in the Salt Lake Tribune. So even today, these red aurora are still a phenomena that scares or has a non-intended effect on people. Okay, so that was the old stuff. And then we started to get a bit more sciencey, and we've heard today from Greg about this too to some extent. The sunspots, in terms of doing something scientific with them, looking at them regularly, 1600-ish. But then they went away for a while, and of course, this thing we call the Maunder Minimum. We'll do more about that. Yes, ma'am? Carefully. I know that we saw a transit of Venus at Cape Cod without glasses or anything. It was a very early morning transit, and it was coming up across the mists in the sky. we didn't need equipment. We could actually look. And there are times when I would think that things are such that you could perhaps see sunspots. I most certainly wouldn't encourage us to go and try this, but do you have any, Greg, any? Well, isn't it worse if you're using a telescope? Okay, that's the kind of thing I was thinking, that there are conditions, and so burning down a forest probably is a good way to do it, yeah. Okay, William Herschel, we've heard today, and I agree that this article was one of the early attempts to correlate two utterly independent parameters at the time, that there was a cause and effect. Do we believe it's a cause and effect, Greg? We do, okay. Okay, so then magnetometers come along, although, you know, some forms have been available before, but the regular recording and observing is what you need. And our scientific kind of community started to do this. But I would argue perhaps the concept of a geospace is associated with the Carrington event in 1859. Carrington observed, although he may have missed the best part of it, a white light flare on this day. But a few miles away in Kew Gardens in London, a magnetometer recorded a kind of signature. And then the auroras were wild all over the place. So the correlation between these events did actually get brought together in the literature and the newspapers. So this might be where geospace got its first real evidence that it was all connected together, between magnetic fields, between the solar emissions of something, and this dynamic phenomena called the aurora. Okay, so then let's just, given that much, let's just create a definition. And I don't think it's very robust, but the outer boundary of geospace is the magnetopause-Bow-Shock, and the inner boundary is the lower ionosphere, this thing we call the SAIR. So I'm just keep on beating this onto you, so if every solar physicist here knows what the SAIR is forever, we've won, yeah? And then the outer boundary interfaces to the solar wind. Of course, that's your CMEs, CIRs, and all these phenomena, while the inner boundary interfaces to the atmosphere, and that's where the flares bang into it and other energetic phenomena. Okay, so that's our kind of working. So to do the geospatial, you need, as far as I'm concerned, a magnetosphere. If it's a planet without a magnetosphere, it's not a geospace according to that definition. Okay. So this is for Greg, or from Greg. His first number here, I've got 1340. Do you know where that number came from? Yeah, I mean, today we saw what? Okay, so don't tell me, Greg. Let's ask the students. What was the solar constant equal to today? 1360, right? So, okay, so they're up to speed. So this is kind of erroneous. It's watts per meter squared. And of course, the EUV during solar minimum drops down to 2 to 3 milliwatts per meter squared. And at solar maximum, it's about 2 to not quite 3 times larger. And yet, this is the thing that is space weather, our geospace response to, not this thing up here. Now, without this, of course, our atmosphere wouldn't be there, which would be, or it wouldn't be the way we know it. So what we're going to do, in order to do something on the past and in the future, I'm going to talk about a model. Ray Robel began this work with a 1D model representing the upper atmosphere and the ionosphere. So it's a global average. And then I had a graduate student who worked on this, and Tian here also. Not necessarily, I'm not sure if Tian was an NCAR or at the university. But either way, these are models that are not three-dimensional models. It's a one-dimensional attempt to understand what would have happened in the past if you could change these things? And so that's where we're going. One could argue that the solar cycle EUV determines geospace climate. And that's kind of what we're going to advance just now. Okay, so some of these plots you've seen already, so we'll go through them quickly. It turns out, for a simple hydrostatic kind of atmosphere world that we're living in, that the pressure system, the pressure coordinate system, is a much more logical one than altitude. So what I want to do here is just contrast the dynamic range of densities. It's the same axes for solar minimum and solar maximum. And it's just looking at our normal atmosphere. We've not done anything to it yet, except solar minimum, solar maximum. And you can see that they're kind of pretty similar, the three main species that we've talked about. But if one goes and looks at the points at which things change over, we're going to see in a minute or two when we get some peaks on here. With these curves, it's not so clear. The slopes should change. When you go to solar maximum, temperature slightly higher, these slopes will change. But the point is, the altitude scales, although it's the same, the range is different. For the pressure level 5 here is 350 kilometers. Here, it's up at 500. And as you put less energy into the system or more energy, this scale stays the same, but the altitude range is affected. Okay. There's two. This came out of a thesis. MSIS 90 is our standard empirical model of our neutral atmosphere. And GATE was the name of this physics model designed to look at different solar cycle EUV fluxes. Okay, so here we go. Review our upper atmosphere present-day climatology. What is the name of this atmospheric layer? The temperature is very sensitive to the solar cycle. So you've got the stratosphere, you've got the different layers, you've got the mesosphere. The thermosphere, okay, that's the name of this layer in the atmosphere, the thermosphere, okay. And here's what what we've seen earlier today, the density of the electrons and ions. Ne represents the sum of all the ions together to form the electron distribution. Now we can see what I was talking about. This is solar maximum, this is solar minimum. O plus is the upper peak, and it's about between 200 and 250 during solar minimum. And during solar maximum, it's up at 300 or just slightly above it. But the pressure level of the peak tends to be at the same place. Okay, so our kind of objective now is what happens during a Maunder minimum or a grand maximum when the solar flux is modified. Okay, so we've got one more plot to show first. Here's a nomenclature. How many of you understand this nomenclature? Anybody familiar with the nomenclature? Oh, okay, then I should just tell you what it is. Well, 250 and 305 might give you a hint. It's the height of the peak of the ionosphere. And HMF2 is the height of the maximum F2 layer. And that's the F2 layer. And similarly down here. And then NMF2 is the peak density in that layer. 3 times 10 to the 5 at solar minimum. And here it's 1.3 times 10 to the 6. Okay, and that's our dynamic range for solar min, solar max. The other one we should show you then would be the temperatures. We've done this before. What's this constant temperature referred to as? Exospheric temperature, thank you. So you can see this is solar maximum. It's much higher, it's 1200 Kelvin. Solar minimum, it's down at 700 Kelvin. But now you again see this bending away for TE, the electron temperature. This is solar max, and this is solar min. And simple question to you is, why are the dayside electron temperatures elevated over the neutrals? Does anybody recall? This is me testing you from this morning. Where's the energy? What's the extra source of electron energy? Photoelectrons, they play a big role in this. When you bring in soft X-rays at 1,000 eV, an ionization occurs, and then there's an electron with a boatload of energy. So that's what you're looking at. Solar min, solar max difference. Okay, I think we're ready. One last thing. The electrons are coupled to a hot magnetosphere reservoir on the top side that has a weak solar cycle dependence. Okay, this is the one that's new. Okay, this one we want to talk about just for a second so you know where we're going. The energy flux, the radiance between about 5 nanometers and maybe 120 nanometers, Lyman alpha. It's what we call UV soft X-rays. And that's the one that's been doing all this ionization. During solar minimum, this kind of point, and here's solar maximum, the kind of temperature in the ionosphere, atmosphere, the exospheric temperature ranges from 600 to about 12 to 1300. And this would be solar minimum, and this is solar maximum. So to do these studies of going to Maunder conditions or maximum conditions, we have a straight line. So of course, straight line means you can extrapolate either way, and you can deduce what you might call reasonable values, well, sort of reasonable values for the irradiance for solar weak conditions, Maunder conditions, and then maximum conditions. So what we want to do is do some calculations and then ask the question, what would that mean to our present-day technical society? Okay, so that's kind of what I'm about to do. There are 4 sets of kind of points on here, and a straight line through them looks pretty reasonable. All 4 represents different empirical attempts to relate the EUV flux to radio flux and other things. So that's how we as scientists represent the dynamics of the EUV spectrum across the normal solar cycle. Okay, so run the global average IT models for S values between minus 0.5 and minus 1. So this is definitely a Maunder minimum type condition. What would happen? What would we even know geospace was affected? And then hint, for about 100 years, humans have developed technologies that depend on geospace. So I'm coupling us back to this morning's lecture a little bit about GPS and other things. So let's just do the calculation. So here we go. You have to kind of remember a little bit. Here's the height of the layer, 250 at S equals nothing, our normal solar minimum. And then we get to these Maunder conditions. And the height of the layer is diminishing. Okay, it's down to 180 now. And over here, the density of the F layer, you can see, is similarly diminishing. So that might be naively consistent with an interpretation where if you go into Maunder conditions, the EUV fluxes are decreasing. This is what happens. And now our question is, what does this mean as far as if this happened to us now with respect to our technologies? So we'll do that in a second. I've put here a little thing that I don't know if anybody knows what a G condition is in the ionosphere. Okay. It's a unique, neat condition that can happen occasionally. And basically, under these conditions, the ion layer, the ion molecular layer, the NO plus, O2 plus, is larger than the O plus. Earlier today, I showed the one with 100 millivolt per meter electric field. The Joule heating can convert the O plus into the NO plus, and you got this reversal. This is what the G condition is. It's infrequently observed, but what this is saying as you go into Maunder conditions, it's almost there all the time. Okay, so let's see what this means. Maunder minimum. Radio waves used today to carry over the horizon radar work will not go over the horizon. So our frequency ranges that we currently use for over-the-horizon radars wouldn't work. Satellite drag, but this is a positive, but satellite drag would be insignificant in today's LEO orbits, which would be a great blessing to the people who have to track every piece of debris that's up in our LEO orbits, and there's tens of thousands. The way in which the ionosphere has collapsed is because the neutral atmosphere has collapsed. I didn't show you that, but it's also much colder. We wouldn't even be worrying about LEO in terms of drag. What would happen is the engineers would launch LEO into lower and lower altitudes. So just now you're up at 250 to 600. During a Maunder condition, you could run your satellites at a much lower altitude. The geolocation would be almost independent of the ionosphere. The factor 10 decrease in electron density, total electron content, would have a very positive effect in trying to correct our GPSs. And this might be the sad part. Marconi's transatlantic first radio communication might not have worked. There's not enough ionosphere to propagate these radio frequencies the way he did from England to Newfoundland. Okay, so it would affect us. Some of it's positive and others not. What we can now do is look at the grand maximum. The grand maxima occurred around 1250 AD. So here we go. You have to play with the S index. It could be between 2 and 3. Again, it's hypothetical, but there's different people who've tried to estimate. The EUV flux may have ranged from 14 to 21 milliwatts per meter squared. Still nothing compared to the solar constant. But nonetheless, what will this do? So we could take a look at the simulations again. Okay, there's 4 panels, so we'll take a second to figure out what you're looking at. The first 2 are almost linear as a function of the energy input, the solar irradiance and the EUV. This is our solar min to solar max range. And what you're looking at here is just an index people have used or created, and it's behaving reasonably linear. So this isn't too interesting other than the fact that it's kind of an index. I use a thing called the S index that we explained. P is just another one. But over here, we have our exo-based temperature. As we get into the exospheric temperature of the neutral gas, here it goes from 600-700 at solar min up to 1200-1300 when you're at solar max. And then the extrapolation, it seems fairly linear. I know there's a kink there, but the trouble is the temperatures are getting up to 2,000 to 3,000 Kelvin. And that's fairly hot, especially if now this is continually. It's not an event. It's not an aurora that's created. It's every day. So down here are the 2 panels that are most informative. The first one is what we call TEC. This is the one that you integrate all of the electrons in a column between a GPS satellite transmitting to you on the ground. And it just takes off. It seems the straight line is even steeper. So it's not this linear curve exactly. So that's the prediction. And we're more than doubling or trebling solar maximum type TECs. Okay, so the next one over here is kind of a real neat example of just because this is linearly kind of increasing, other things might not. This curve here for O+ represents the peak density. It saturates at a value. And the way you explain the total number of electrons increasing, but the peak density not increasing, is because our temperatures are rapidly increasing. So the actual shape of the profile, the peak's locked, but the densities keep on increasing. Everything else seems to follow that same trend. Okay, so for the extreme maxima, HMF2 height is really going up, 360 kilometers to 500. Sorry, I didn't show that one. But the O+ peak didn't. It's pretty much maxed out, saturated. However, TEC kind of went up really, and the exospheric temperature increased. So we're looking at something like 3,000 Kelvin, and the question is, how important is that? And as we go through the talk today, we'll see some other numbers. If we get up to 5,000, hydrogen just blows off. We lose our hydrogen very quickly. So 3,000 is starting to be worrisome. Okay, does space weather impact our climate? So we're moving kind of forward. Today there are three main aspects of space weather that can supply enough energy in a space weather event to disrupt geospace climatology. So the aurora, which we talked about. The X-class flare we haven't talked about, and we're going to introduce that in a second. And then Joule heating associated with very large magnetospheric cross-tail potentials. So these are the three ways in which the sun can generate space weather. I know there's CIRs, there's CMEs, there's mechanical phenomena in the solar wind that get to the Earth. And what we're saying is once it reaches the Earth, what will it do? And it ends up in these kind of forms that it affects geospace, how the energy is kind of modified. So what I want to do is the following. I've got a plot here of thermal energy density, and I'll define that in a second. And here's our altitude. And here, of course, is your magic 100 to 120. And what I've got on here is total energy, and then N2 energy, O2 energy, and O energy. So the separate curves aren't too significant. But it's this blue line, this light blue line that we want to look at. As you go deeper into the atmosphere, the energy content, the number of joules per meter cubed is increasing. But let me define what I mean by energy. It's a very crude analysis. All it's doing is saying combining neutral density and the temperature produces the altitude distribution of only the thermal energy density. So that's the 3/2 kT form. It's not worrying about how much energy there might be in rotational or vibrational states. So the numbers could be larger. But that's how much energy is just being held in the atmosphere at different heights. And what we want to ask is, under really severe geomagnetic storms or flares, can we even get close to these numbers? If we put in an amount of energy in a storm that's way down here, it's not going to affect the atmosphere. The hydrostatic approach for the atmosphere will work fine. But if we put in a chunk of energy that sits this much in a reasonable length of time, such that the hydrostatic situation is broken, and we have to go to hydrodynamic, what all can go wrong? So we want to ask the question for flares, aurora, and Joule heating. Can we impact the ionosphere? And if we do, where? Well, I keep on pointing here, so you know fine well there's a bias that where it's going to happen. So that's kind of what we're looking at. And during a space weather event, is there sufficient energy deposit to cause a hydrostatic climate scenario to become a hydrodynamic problem? Now, this isn't going to, Greg's not going to worry about this yet, because all of our space weather that we have in our environment only lasts for a day or a few hours as a substorm. But there are M-class stars that are continually dumping out millions of more energetic flares and CMEs and things. So ours is a kind of nice world still. So let's just see how nice. What's this? How many of you have seen a picture like this before? 1, 2, 3, come on, 4, 5. Where was the camera located when this was taken? Yeah, it's a satellite up in space looking at the aurora. But this is why it's called the auroral oval, right? Now, when the oval was created, the terminology, we had no satellite pictures. It was data from ground stations assimilated. But in actual fact, during a storm, there's 12 minutes. So they're 1 minute apart, not quite, 59 seconds. But these are photographs. Now, to some extent, the dimming isn't because the aurora suddenly changed. It's because the satellites kind of moved closer in, okay? But this is a good example of an auroral oval during a storm. You can see there's energy being deposited at all kinds of local times. Okay, I should hit one more button here. Sorry, this bright side of the picture is sunlight, okay? So we're seeing UV from this side of the Earth that's being sunlit. But the question is, in the middle of this kind of aurora, somewhere inside the auroral oval, how much energy is being deposited in a certain length of time. Now, this phenomenon will easily last for 30 minutes. So you've got 30 minutes in which energy is being deposited, let's say, in a region. And the question then is, how does that affect the atmosphere? Okay, so one more figure that you may or may not have seen before. This is energy in this direction, 110 keV. Remember earlier today we talked about the aurora having kind of different characteristic energies. We looked at it as 6 different monoenergetic beams. But these are rocket measurements during aurora. And the different curves show you, to some extent, the variability of this. But between 1 and 10 kilovolts is where most of them are. And the calculation I did, or I'm about to do, is using A as the typical one. I know it's not quite typical, but let's assume it's one of the stronger ones. B, I don't want to use because B is above 10 kilovolts, and it's going to dump energy lower down. Lower down means that there's a bigger energy reservoir already, and the sensitivity is not going to work. So with this spectrum and the kind of intensities that we saw in the images, we can do a calculation. And what we find is the auroral deposition for that spectrum is over this region. So the ionization is over this region. But more importantly, this line represents how many joules per meter cubed I'm putting in. You need to know a little bit more. So I've integrated up the spectrum from 95 to 120 kilometers. And I've assumed this aurora stays stationary for 10 minutes. Now, the auroral images that we showed the movie, there was no stationarity in the aurora. It's moving all over the place. So here's one of the big problems we modelers suffer from. We put into our model an auroral oval, and we say we'll use the KP index. What's the frequency of the KP index? 3 hours. So every 3 hours we change it, and we run our simulations. So it's a real hard thing. When you see the aurora all dynamic moving around, you then see auroral images, and then you see what I'm doing. It's not self-consistent completely. But nonetheless, the kind of energy being deposited is enough locally on the time scale that the atmosphere can redistribute that the problem becomes a hydrodynamic problem. You're bashing this atmosphere hard, and energy propagates mainly upwards. Waves propagate upwards. The composition starts to get mixed. And in particular, the regions up here start to see changes in the atmosphere. And the one that's most relevant, if you like, is satellite drag. You putting energy down here leads to satellite drag up here that's very, very measurable. The CHAMP satellite we talked about is a very good example of these measurements. So the energy goes in down here, modifies the neutral atmosphere. So, okay, I'm going to talk about flares. This combines a number of talks. This is Greg's part of his talk. This is wavelength, 100 nanometers, 1,000 upwards, okay? So the black body curve looks like this. And then we have a 10 to 100 nanometers regime, and that's our UV. And then over here, we have these hard X-rays, and in here, what we call soft X-rays. The active sun and the quiet sun are quite different here. But when you put in a flare, it's down here that the flare is extremely active. Oh, these are orders of magnitude as you go up. So there's almost 3 orders of magnitude for this one example. This is about a 40-year-old diagram from a rocket flight data combined with other information. But this idea that when you get flares, the energy goes in primarily in the X-rays or the soft X-rays. The UV does show a response, but it's not ginormous. So this is what we want to talk about. And what does that do to the atmosphere the way we've been working? Yeah? Oops. Photons in the 1 to 10 nanometer range are most geo-effective, and that's just what we've said. And if I could do the same calculation I did before, computing the energy input over an altitude region, we see that the flare is, and this is one example of a flare. It's called an X-class flare. It was actually an X-class 5. So it's not the biggest we've ever seen. But most certainly the energy deposition over, you need to know how long it was running. 20 minutes, a good strong flare will stay above some energy level for maybe 20 minutes. So in 20 minutes, I can put this much joules per meter in locally. Now, the flare is the whole day side, and of course the solar zenith angle is important as to how the energy is distributed. But it also has enough energy to change the atmosphere locally and hence above. Let's go to the third phenomenon, which is the electric field. This is just a schematic representation. The Earth's kind of down here with some continents. But these yellow lines represent what we were talking about this morning, the two-cell convection, which is kind of a standard way of representing it. It's an oversimplification for anybody who's working in the field. But nonetheless, it gives you an idea. There's an electric field across here. There's auroral currents. There's the Pedersen currents flowing in here. And the question then is, as the currents come down, the currents go up, there's auroral electron deposition, the conductivities change, the Pedersen changes, and all through here you've got a wide distribution of electric field values. So that we've got all the conditions we need to get Joule heating. So the question is, can you, with reasonable electric fields, and this are Hall and Pedersen conductivity. Here's your Pedersen conductivity, and here's your Hall. Being increased, if you like, or energized during an auroral event. And with conductivities like this and 30 to 100 millivolts per meter, what can you expect? Well, Joule heating has the majority of the magnetospheric energy being deposited into the atmosphere. And what we've done here is between 100 and 140 kilometers. This kind of Joule heating way exceeds the local energy deposition. Now, I've assumed it's present for 3 hours, and that's a rather longer time than necessary. But clearly, any fraction of an hour puts energy in locally into these regions that exceeds the local, which means our local modeling of the thermosphere isn't going to work. It's a hydrodynamic problem. Waves are being generated. The composition is changing. So space weather is doing this to us and affecting the LEO, the low Earth orbit above you. Okay, so present-day space weather does disrupt geospace climatology on short time scales of hours to days associated with a specific space weather event. So the things that kind of happen here are the tracking of LEO satellites and space debris is disrupted. The amount of space debris, even objects, fractions of a millimeter are important, because if they're moving at 8 kilometers per second into a vehicle that's moving at 8 kilometers per second towards it, the damage is ginormous. And if it's a larger object, who saw the movie Gravity? Yeah, how many of you believed it? Okay, okay, so we said it. Yeah. But she was quite nice, wasn't she? Okay, so geospace, GPS geolocation tools are disrupted during such periods. And this was the case with the WASP system, and it's still the case if we got a real major storm. We've been going through this solar minimum period that's been very long, and the ensuing solar maxes haven't been very dynamic. That we've not run into the big storms we ran into 30 years ago. We need these kind of storms to really disrupt our systems. But humans get the pleasure of seeing geospace's beauty at mid-latitudes. If we really did crank up, got these grand maximums, double solar maximum, we'd be seeing aurora every night. That'd be just wonderful, right? How many of you live at mid-latitudes? How many of you live at equatorial latitudes? Okay, sorry, it's not going to quite get down there. Okay, so let's back up now and look at the climate on a bit more extreme case. I come back to this figure because it talks about the solar constant, the EUV, which is the solar cycle kind of dependence, and space weather, which is the bottom end of this. So let's just bring up this next kind of plot. Dana will correct me if I say this wrong, but he showed us on Friday that the main sequence stars associated with where the sun is, there are B-class stars and M-class stars. And he was just contrasting on the diagram stars to the right, to the left and to the right. Basically, the B-class stars are very, very hot. So this affects Greg's work. Instead of this, we would get a quite dramatically different atmosphere. Your climate, Greg, if the sun was at 20,000 Kelvin, can you predict what it looks like? Okay, so while Greg's doing this, let's continue. There's no dynamo or negligible dynamo. There's no EUV or space weather. But there is this problem for Greg, that this isn't going to sit here. It's going to move this way. And our atmosphere from which we start, and we assume it's a constant, and quite rightly so, isn't going to be like that. So anything in this direction leads to our very fundamental atmosphere being a different problem altogether. Once we get to 6,000 Kelvin, it's our sun. And the system as we know it is what we have. We have, because we've got dynamo on the sun, we've got magnetism, and that results in all of this stuff, which has nothing to do with the black body that we've heard about. We aren't talking about this top end because, I don't know, we've got enough to talk about down here. But the solar cycle is this piece, and then the space weather is this. So we're familiar with what that looks like. But if we go to the M-class flares, and a lot of the exoplanet people like to talk about this, especially if they're worried about space weather being important, because down here, from Greg's point of view, we're a very cold sun, and our atmosphere would then respond to that. But the worst part is now, the dynamo system on that star is huge, with abundant EUV, and therefore space weather is really extreme. And Chandra and telescopes like that looking at these kind of stars see flares that are millions of times more intense than our flares. So this world, we're maybe not too happy with this, but this is problematic. If flares are coming all day long, they will affect Greg's atmosphere, not just that. So this is our kind of scenario of we have our nice geospace, but under these conditions, it's an entirely different geospace. Coming back to that geospace, we could say, well, the Earth wasn't always in this environment of a sun at 6,000 Kelvin. The curve, if you like, that's kind of inferred. This is us today, and this is giga years going backwards in time, if you like. And this is our exospheric temperature. So this is a computation. Sorry, I misplaced the reference. I haven't got it here. It's in the book. But basically, I've added the word B-class stars based on what we heard by Dana. And again, this would be the environment we might fear if we had a B-class star at 20,000 Kelvin or some much larger temperature than our sun. This axis is really important because at about 5,000, we get hydrogen blow-off. Now that's the easy one. As our temperature ramps up, we have a hard time getting it up to 3,000 on a consistent basis. But a grand maximum starts to get you up here. But if we ever got up to there, basically our hydrogen outer layers of the atmosphere would be just gone. Thermally, they would have escape velocity. So Jean's escape would be effective, and hydrogen would be gone. Now, clearly, if you run up this a little bit more, and I have markers on here, our O plus or our neutral oxygen start to bleed away. And depending how far up this curve we go, that's an important player in terms of what's going to happen to our atmosphere. In fact, the question is, in these earlier billion years, what was actually going on? What was the atmosphere doing? What was the loss rates of the atmosphere? So we don't want to go backwards in time. Well, it even gets worse because the other property that we haven't included yet here was CO2. Whereabout is there a lot of CO2? Thank you. That's another planet, I agree. I was hoping for another planet. Let's try again. Venus and Mars. Their atmospheres are heavily CO2 orientated. Okay, at these earlier times, the thermosphere contained CO2. Our atmospheric modelers know this stuff. But it's an excellent greenhouse gas in the lower atmosphere. But in the thermosphere, it acts as an infrared IR radiator. So high up where we're talking, it's able to take energy and send it out into space as infrared radiation. So the neat and maybe ugly part of CO2, it competes against the extra heating. So if we're at these earlier times where the energy input in the EUV is much larger and we have a CO2 atmosphere, in actual fact, there's an equilibrium that's going to form, and we're going to show that in a minute or two. But CO2, does anybody remember, Dana put up plots of the upper atmospheric temperatures for Venus and Mars. And their exospheric temperatures were way cold compared to our own. And to some extent, we've got a kind of source for that cooling. Okay, here's a complicated plot, but we'll spend a second or two trying to understand it. This is the effect of the cooling from CO2. Here's our exospheric temperature, and this line is us today. Now, there's a whole bunch of lines drawn on here. The dotted line across here is the one that we've been talking about. If we get above this line, our hydrogen exosphere, if you like, is blown off. Now, we still have one because today, this line here, at this point here, crosses the point of, this point here is today's CO2. So it's normalized to 1. That's our present day curve. Now, that's us here. And if we start doubling the XUV, this stuff that we're talking about, the temperature starts to go up. Okay, the effect of the cooling doesn't cool it completely. We get up to about 4 or 5 times our present day, and we would reach that 5,000 mark. Okay, but if instead of just the amount of CO2 that we currently have, we have something like 1,000 times more CO2, then our today's temperature wouldn't be 1,200 at solar max. Solar max would be down at 500 Kelvin. So, and that's because the extra carbon dioxide would be radiating out energy that's coming in. And in that scale, our hydrogen would stay with us up until we almost had 20 times more EUV. So that the use of carbon dioxide, nitric oxide, water in the upper atmosphere is to compensate against just simply putting more solar EUV in. We can cool it down with these. But we shouldn't start forest fires just for the sake of it. Okay, so changing the subject now. We've been heavy on the atmosphere and the ionosphere. So geospace also has a magnetic field. What's happened? Oh, a break would be a good time here. Yes, thank you. No, that was still. Oh, but that's no, like Alan, we both agree. But that doesn't mean anything because yeah. right. Okay, let's start up again. Guys, you only have half an hour left, so we'll be good. Okay, so we are going to talk about dipole field flips. Clearly, the topology that we've been talking about for the geospace is that the magnetic field orientation of the dipole is pretty much as we know it today, and hence the energization mechanisms producing aurora, the electric fields where they map down to, are defined by that geometry. So if we start messing with the orientation, then the possibility of energy being deposited through aurora and electric fields in other places becomes interesting. Okay, so that's kind of where we're going here. So the virtual axial dipole moment is the piece of information that we're going to look at. There's lots of research going on. This refers to an attempt to just look at the one component and hopefully the dominant component, the dipole component. Clearly, people realize that during the flip, other things might be going on. It'd be interesting to get the other components or other moments. But at present, the database is primarily this VADM. Okay, so let's look at what the recent past history looks like. Today is on the left-hand side, and the alternating black-white represents what you call periods of flipped dipole orientation. And million years, you can see hundreds of thousands of years, very kind of frequent, but there's nothing systematic. For example, the Cobb Mountain flip, if you like, actually turned out to be a double flip, or appears to be, depending on where the data's taken. It happened forward, backwards, forward. So that was in a very short time period, but that's it's not very periodic. There's no attempt to kind of deduce a period from this kind of data set. What we have is, good information that there were very clear flips. And the other piece of information we have is how large was the dipole moment that we were finding in these samples that people were analyzing. So 0 is our time of the flip. This is before the flip and after the flip, or post-reversal. And these are examples for some of these flips, where the information we're kind of looking at here is somewhere around 8, or 6 to 10, if you like. And this is our amps per meter squared, in units of 10 to the 22. So this is we're currently about 8 of these 10 to 22 amps per meter squared for our Earth's dipole moment. So most of the time in the past history, we kind of start off with similar numbers, and then it flips. It drops to 1 unit. So it's a factor of 10 difference from where we are today, kind of, to what we would need for a flip to occur, based on the empirical evidence, if you like. And then after that, there's a slow return. And there's a lot of structure in here, but the bottom line is there's a consistency, at least, that when the flip occurs, the dipole component is down to just a little bit, maybe above 1 times 10 to the 22 amps per meter squared. Okay, and if we kind of go down here, at the time of the reversal, what actually happened? Was there higher order poles, generate quadrupole, octopole magnetic fields? And these are open questions. But in summary of what we do kind of have, the factor 10 decrease from the maximum to the flip value. Here's your flip value, 1 times 10 to the 22. The largest is 10, and we're currently at 8. So depending on how you want to interpret things, we're safe for a while, or else we're starting on the decline, depending on what data you look at. So many examples take 60 to 80 kiloyears for it to decrease to the flip value. So this is the kind of window of time from our present day value to this this flip value. So is the Earth due for a B flip? And it doesn't look like it's too imminent, not on our lifetime scales. In the Friday's magnetosphere lab, we used, there were various simulations that you had access to, and one of them was a 1/10 dipole. And that was kind of based on this kind of thinking, that you go from our 8 to 10, value 10 to 22 amps per meter squared dipole moment, and drop down to 1. And that's why you were doing the simulation with 1/10. Was there anything interesting that you noticed when you dropped it to 1/10? Sorry, I'm pushing on you guys. I know you did the lab. Some of you saw this. Okay, good. But if the day side's smaller, it does impact the rest too. Was the neutral line, did you look at that or no? It was shorter, okay. And the whole system collapsed in. So you were kind of exposed to what the magnetosphere might have looked like. Now, there's been attempts to run simulations with the BATS-RS with quadrupole fields and octopole fields. But that introduces a whole bunch of really neat geometries that are really hard to interpret. But the one of just dropping it to 1/10, you saw the consequences. This is maybe today, and this is the more recent past kiloyears of the Earth's dipole moment. Again, it's the dipole field. And here's your 10. So it's got up into here. This is thousands of years, 10,000 years, 2,000, 3,000 years ago. So the argument is we're in a period of declining B field. This is a 2 sigma piece of information, this spread. So we're 2 sigma. Seems that we are on a trend that's gone from a high of 12 down to 8. And here's our target. You're not going to do it in your lifetime. You're okay. Okay. So Friday's lab, you did the reduced. But the angle between the dipole axis and the rotational axis is also very important. If you bring it to 90 degrees, then the dipole axis at times of the day is looking straight at the sun, if you like, and other times as the Earth rotates, it's looking at 90 degrees and other angles. And the magnetospheres then are formed and ripped apart all day long. The current systems are changing. So the question is, under these conditions, the SARE still exists, but locations for the aurora or Joule heating will continually change. The sunlight is still there. The energization mechanisms, unless they're dramatically different, would still have auroral type of energies. The electric fields we get, because we're only extracting so much energy from the solar wind, we would still end up with this thing called the SARE protecting the lower atmosphere. So just very quickly, this is a cross-section of the magnetosphere. The Bow-Shock standoff distances are out at 10. And if I go to the next one, this is the 1/10 B field. And you can see everything shrunk in. The neutral line, let's go back. The neutral line isn't even on this, it's out here. So that the simulations that we can do today can actually do a reasonably interesting job of what happens under these kind of hypothetical conditions, including replacing a dipole field with much more exotic B fields. And that's available. Nick has created a suite of these model runs to let people look at them. Okay, then the other thing, of course, you can do similarly is to take your dipole axis relative to the rotation axis and tilt it. And this is an example of 35 degrees. But this is a snapshot. So as the day progresses, this point becomes this point, and the entire magnetosphere starts to flip and flop on a 24-hour basis. in a very marked way. Currently, our offset is only 11 degrees in the northern hemisphere and somewhat larger in the southern hemisphere. But even so, we have a kind of wiggle in the magnetospheric geometry. Okay, so the last topic we're going to touch on is the solar wind. Everything we've talked about so far didn't touch on the solar wind at all. I haven't brought it up. We've talked about a magnetosphere as a pretty hard body. We've alluded to things like CMEs, CIRs, and somehow we extract 20%, 10%, 20% of that energy, and then the magnetosphere does its own thing. But the solar wind is there the whole time. So in some way, the equilibrium that geospace is in is also defined by what is the solar wind doing to us. And again, we can attempt to look at the past and see how different the past was. So the solar wind speed and density are two key parameters. There is an IMF, a magnetic field, interplanetary magnetic field in that too. And as far as turning on and off geomagnetic storms or aurora, or how strong these storms are, the magnetic field is really important. But just the pressure, the speed, and the density are kind of important parameters. The reason we might argue speed and density are important is because you can look at other stars and in some cases actually see this. The magnetic field, even in our own environment, it's very hard to, in the solar wind, determine the orientation of the magnetic field, and that's the all-important part. So these two parameters are perhaps more accessible. So the idea really is, even among astronomers, there's a real effort out there trying to understand what solar wind's parameters look like in comparison to ours, and what's the main sequence variability in this. So I have another plot that we'll put up. Is that yours, Dana? It's my one. Can you take my bag outside? I don't have a cell phone. My wife gives me her cell phone to take with me, and I'm not too careful. I didn't switch it off. Is there a button to switch it off? Okay. Okay, so this is an example of, here's again today, and you go back billions of years, giga years, the solar wind density. So the solid lines are estimates of the solar wind density. And down here is what you would call today. And that's not untrue. A few per cc, maybe 10 per cc. Oh, that's per meter cubed. Yeah, that's right, per meter cubed. So 10 to 7 is about under 10 or about 10 per centimeter cubed. So that's kind of correct. And on this axis is the solar wind velocity, and that's the dashed line. So the dashed line, 400 kilometers per second. Again, we've seen that. But it turns out that during coronal mass ejections or the fast solar wind speed, the numbers range up and down through here for events. But this is the background solar wind, the climate version, that our magnetosphere would have to kind of just come to equilibrium in. So this is a star that's been reasonably accessible, where people have been able to measure or infer from their optical measurements what the solar wind density range is and what its speed is. So this kind of work is ongoing, and that's the one way in which we can learn about these environments. If we can learn if this curve is even reasonable, we can turn the thing around and infer what kind of geospace environments for what kind of magnetic fields we have. So here's our dynamic range. You can see as you go further back, these are logarithmic numbers on density. So as you go back in time or to these other stars, these densities, a factor of 100, 1,000 times larger in the solar wind. You can imagine our geospace boundary has been quite different, especially since it also includes a gradual increase in the solar wind velocity that's bombarding geospace. So our geospace can learn a lot from other stars, especially if we understand how our early star behaved. Okay, so I'm getting towards the end here. So there's again a takeaway message. And the takeaway message is that what is it that heliophysics can learn from stars? So I'm not asking you to do it now, but the kind of talks that I've given, there's a lot of questions we have about the past or the future of our geospace world, our upper atmosphere. And to some extent, the stars tell us a lot about these earlier years or future years. So once we get that kind of information, and we've just talked most recently about something as simple as the solar wind speed or its density, we can most certainly take information like that and do what-if scenarios with our present-day modeling. BATS-RS is just one really neat example. Its dynamic range of flexibility and input is fairly stellar. And I don't mean that, maybe that's a bad pun, but you can push BATS-RS rather hard. But then, what is it exoplanet research can learn from heliophysics? Well, we turn the tables around. If you strategize what an exoplanet's atmosphere might be like, and you say something about the stellar environment it's in, we can most certainly, with just that kind of information, literally reconstruct the environment, the atmosphere, the ionosphere, if it does or doesn't have a magnetic field, what would it look like? So the habitability for a modern technology versus just simply the environment, we can actually contribute a lot to that. The word Goldilocks is a very back-of-the-envelope analysis. We can actually do a lot better, especially from the point of view of things like space weather events, which are not your black body solar constant as the dynamic part of a star. Then this is your real takeaway. For the rest of your lives, you've got to remember this. The SARE. It protects the lower atmospheric space weather, flares, aurora, and magnetospheric electric fields. All the very energetic processes that go on, which we call space weather, really do impact our technologies, but very little of it gets down. I know cosmic rays and very energetic particles get down deep enough that if you're in an airplane flying at 30,000 feet over the poles, you can at times experience radiation levels like, I guess, a dental X-ray or something. So that there are effects other than the one I've just mentioned. But by and large, the bulk of that energy is going to affect our technologies, our satellites, our communication systems. So extreme ones could be very detrimental. But lower down, we still have an umbrella or a shielding against these very energetic things. It's very few flares that would actually come through and really dump a lot of energy in the atmosphere at a place other than up here, where it can really do significant damage to our environment. I'm done. Thank you very much.